Welcome back. How's it going? This is the last class before fall break. It's exciting. All right. So, just a couple notes on our plans. Today, we're talking about. I'm going to do another test discussion real quick. Want to not let the question that you answered on the extra credit go to waste. And then we're going to talk about measurement invariance, kind of an important feature of structural equation modeling that sort of could be overlooked based on what I've told you this part. Then next week is not class because fall break. The week after that, we will do the structural equation modeling lecture, which will basically be that end of the first lecture. But I think I'm going to modify it with better simulation, do IRT, build it together, maybe have to look for measurement invariance, and put a lot of the topics that we thought about together across the class. And then finally, the last week, December 10th, will be your presentations on the homework or your analyses for what we do. Or again, those last presentations are going to be on Zoom during our normal class period. I'll have more details about those when we get into December. But basically, what your homework answers were, if there were any problems, just correct those and present what you found, what you did, what you found. But basically, it's about 10 minutes per presentation. So nothing that's hopefully overly long. Yeah.
So presentations are
the 10th. The 10th. The last non-final day of our class. Yeah. Because I didn't ask to have a final scheduled. So the backstory for it is you have to sort of schedule finals and yep. And who wants to do presentations during finals week? Yes. It seems like the last few years, again, I'm trying to strike a balance. When I've done presentations or oral finals during finals week, there's a good portion of the class, well, I booked a flight or whatever, and it's like, well, yes, but it is the final, right? Like, and I remember, like, when I was an undergrad, how that would have gone over with my professor. Hey, but the end story is that there was no authoritarian comeback. It was we figured out a time we could make things work. It was no big deal, but this ensures that everybody can see everybody's project that way. So, yeah, okay. Going back to the last week, then. So everybody turned in the sort of corrected assignment exam. I went through those this morning. You should see your new updated scores on Icon. If anything is wrong, let me know. If my math went wrong or mistyped something, please let me know. And if anything else is wrong, let me know. I can fix it. But I wanted to spend some time talking about that last question, sort of the psychometric evaluation, but I wanted to wrap it in because we're in the middle of sort of measurement models in our class. And this is odd part because SEM is part lots of regression analyses with no measurement whatsoever. That's path analysis. And part, we need a measurement model to go and put a latent variable into those regression analyses. Right? And I think part of where the balance in this class, I'm trying to seek a balance is, it's not just purely the regression exercise that the path analysis is, because the measurement portion is really unique in and of itself, right? The way we define a latent construct, the way we look at it, the way we think about it. And a lot of that measurement part is what you can sort of take out and say that our program, the educational measurement statistics, the measurement portion of it should really be focusing on. So it's part of that. So let's start by talking about that last question. And then at the end of that discussion, if there is a long discussion, we can talk about any other questions you might have in the exam. Okay? Okay. Last question said, do sort of what are the things you need to think about? Let's think the setup once again. I'm taking your exam score, which was indexed by the number of correct responses you had out of 50, turning that into a percentage, and then saying that score is measured against certain cutoffs that I've established in my syllabus to say which letter grade your class should be. We do this all the time without thinking about it. It's been done since you were probably having grades in your classes whenever you were younger, right? And it's funny, we think about, our modern society, how long does that practice date back for, too, right? That's got to go on for centuries, potentially, as well, too. So what I'm trying to establish is, I don't think I did anything atypical when it comes to how we do things in the classroom. But then let's look at it with a psychometric lens, right? So now what we're saying is, oh, I constructed an exam where each item, because I'm creating a single score out of this exam, each item now purports to measure some construct. What construct I would call it? I would probably call it competency with class material and SEM, something very broad, right? Nothing very detailed. It's a hard thing to think about, but okay, so does that sound so far not controversial so far, right? Okay, great. I think of the 50 items, with the exception of the 2 that I omitted because they were not worded and nobody could ever look at how those would map onto the construct, I think it's the first thing we'd want to do is, do the items align with what we're measuring? I think the answer is probably yes, right? On the sort of what we would say a construct validity, I didn't get into validity arguments. There are classes that will do that if you want to do it. But this idea that on the surface, if I say these items are measuring, things from my course in SEM, and they are, would you agree that most of the items, again, except for the misworded ones, fit that? Okay, so we're checking off the psychometric list. All right, we've defined the construct, we've checked the items for it. That's about where we can stop with the positives, right? Because there are certain things we would have to ask afterward to really believe that that score I gave you is correct, right? So yes, we decided that we can all, again, I'm sort of asking leading questions, so I know you don't want to go and disagree with me on anything related to your grade, and it's okay. Your grade's your grade's your grade. I'm not going to change it, but also I understand that. So let's just say that. Let's just say, assume for the sake of argument that you say, okay, yeah, the items look like they came from something in your class. Good, check. The next question is the statistical argument. Do they fit one factor? That's this asking the same question, but now statistically. Do we have statistical evidence to suggest they all measure the same construct? That is indexed by our model fit statistics, right? If we were to think about this, if we were to build a latent variable model with it, and we took each one of your items and your correct, incorrect responses, we would have an IRT model we could use, right? Right. So each item, we could go into Lavon, we could actually run an IRT model. 9 people, I don't think we'll get very stable results, may not even converge, but we could have done that. We would be after the model fit statistic. Why is that important? Anybody want to think about? If it doesn't fit, what does that threaten from our use of our score? Right. So if it doesn't fit, it says specifically these items aren't measuring the same thing. Or at least one or more of them aren't measuring the same thing. We need more either latent variables or control variables or residual correlations, something to sort of balance it. But then regardless of fit, I just added up all the items. Mm-hmm. And if some of those questions really measure some other construct, that's a problem too, right? Now, my one score is not really accurate for what I'm intending it to be, whether that's a construct such as, general statistical knowledge that maybe I didn't provide you in the class, or some other background knowledge, something like that. So that brings into question, should I be using so I don't have that. I can't really easily do that off of 9 people, but you see where I'm going with this, right? Trying to create a validity argument as to what the test use. This is what we do with a lot of assessments in the real world or measurement models as well. Okay, great. The other thing that model fit tells us, we should or should not be adding that to the score. So we need model fit. Additionally, we may need I'm now adding every item together. So let's imagine every item does fit, though. Let's imagine we get good model fit with one latent variable. Let's just imagine that happens, right? For sake of argument. Great. I'm now additionally assuming, because I'm adding every item up and they're all counting for the same number of points, that each item equally measures the latent construct, right? Do you remember the name of the model that sort of gave us a correlated factor score of 1 with the sum score? Do you remember what that name of the model was? It's parallel items. So what we're assuming about our model is not just it's one factor, that it's a one factor parallel items model, which means all the loadings are equal, or discrimination parameters, and all the thresholds or intercepts are equal. Not thresholds, excuse me, residual variance.
Roche model, or is that not bad?
So a parallel items model. So let me back up. A parallel items model in a CFA context assumes the factor loadings and the unique variances are equal. If you were to look at a Roche model, first of all, Roche treats data as categorical,
Sure.
right? So that means there is no unique variance to set to be equal, although they're technically set to be equal. But second, Roche also has that link function. So a Roche model is like an IRT version of a parallel items model, but the latent variables will be on different metrics because one's in logits and one is on the scale of the data, effectively, or scale of the standardized values that come from it. So yes, you are right to think Roche and parallel items are synonymous, but parallel items would have to be the logit function causes a sort of the nonlinearity in test score compared to theta score. Going back to that though, parallel items CFA model is what we'd have to really fit, because now that's an assumption that's really hard to meet. Really what I'm getting at, right? So now we're building our argument. We're saying for that test score, for me to use that for your grade, I've got to believe all the items, conceptually measure one thing, statistically measure one thing, and that the properties of the items are equal across all 50 of them. How do you like that? So now, what do you have to tell me about the test? That's on top of the idea that some items, if you think about it, guess what would happen to an item? And I know my wording of my items, I'm not a great item writer, but if I write an item that's confusing to you, or confusing to all of you, and there are some like that, guess how that item perform? How do you think that item might perform based on the latent variable? Right? If you're basically don't understand it, so you're providing a response that is not truly because of your knowledge, but because it's literally you can't encode, couldn't decipher what I had asked you to do. In principle, whatever theory what we could be measuring can't relate to it, right? So it's likely to have a low loading or a lot of noise to it. Like in an IRT model, we might want a 3PL for that, or something along those lines, right? A lower bound of the probability you get it correct. So what I'm trying to say is, when you start looking at the way that we assign tests and scores in the class, it's heavily there's heavily laden with psychometric assumptions, all of it, and yet somehow we still have to do it. And therein lies the thing I wanted to dwell upon here. There's no real absolutes, unfortunately. There are better ways than others, but let's finally go one other step further. Now let's see what you think. What did you think? Those are my. If I were to answer that question, that's what I did. Did you write anything differently in your answers? If you did, would you like to share? Yeah.
Well, I will share. So I took the route of saying, number one, we had nowhere near enough data to analyze it. And then I took it a step farther where I created many different latent variables collecting those items that I thought, okay, this is kind of like this piece of the class. This is this piece of the class, and so forth. And so that way I can say, oh, did these items really measure this piece that I think? And then I had a latent variable for the ability, of which the latent variables that were collected all mapped onto that, to see if that truly did indicate the ability off of my previous result. So
Yep. So you sort of looked at it and said, yeah, I could conceive of maybe different latent variables for sections of our class. Yeah, that would also be valid. Yeah.
One of the things that I said, which is probably a little more conceptual, a little less mathematical, was correlating the exam scores with our performance on other in the class.
Yeah, like
To show that the performance was either similar, or if it deviated significantly, then that indicates that that's probably not a very good single.
that's a good one. Yeah, I like that too. Anybody else? What about the concept of time? Now, thankfully, everybody finished with ample time, but it is a different environment when you know you have a finite amount of time. Even if all assurances aside, you'll be able to get the items done, most likely be able to done on time. Another latent variable we could think about is your either perception of time or how you perform under time. Sometimes in the assessment world, we call that speededness, right? An exam that's hard to complete puts different demands on you for expressing your ability than one that, you can have ample time to do. Right. And then so it's hard because there are certain things in life where speededness is a thing that's involved in the ability you're trying to measure. So, for instance, making medical decisions in split seconds might be something that you need to consider for nurses or doctors or whatever, right? But that's for what we're assessing here, not important. In fact, speed, like the threat of time, I think interferes with it. So you can think of it. Some people think of it as a different latent variable. People think of it as maybe a bit of like how much overwhelmed you are by the ratio of how many questions to the clock itself. So another, basically threat to the validity of what I'm using it for could be that. Yeah.
Or even a fatigue factor. Okay, I was fresh at the beginning, but by the time I had
Yes.
by the time I got all the word problems at the end, my brain is mush.
Yeah. I should have switched the direction. Yeah. I should have switched the direction. But that's exactly right too. Yeah.
But that could have changed how. But then again, maybe I would have done worse in the earlier ones. Like that doesn't become that order.
Exactly. So when I look at my exam, I've told you this is sort of me trying to figure out how to teach in a class like this in the era of where you can get a lot of help to do a lot if it's all homework based. I'm trying to look at it from a lens of it was an interesting learning experience for me as well too, right? To see the range of scores, to see the items that people had struggled on, and think about what I'm doing differently. So in part, I like the data I'm getting, but I hate the stress that goes with it. So I have to find a way to balance both. I'm going back to now my own teaching practice, but from a classroom perspective, then let me ask another question: what do you think we should do? Like, okay, so we have all these psychometric concepts that we can outline to say, I'm using an exam, a psychometric instrument, in a very high stakes manner to give you a grade, which is a very important deal. Arguably in grad school, it's a little bit less important, but I know that you all don't want to get a bad grade, and you need to get a certain grade at least to continue in your programs, but it's still important. What do I do? Like, clearly, there's a mismatch between psychometrics and what we have to do. So there's a point where assessment or psychometric theory stops, and we're now, wow, okay, so we're going to have to acknowledge each of these might be a problem.
So, I understand it.
Yeah, yeah.
One of the things that I think would have really helped both myself and I think some of my peers, no examiner would be a review period like upfront. So while like I know some teachers think that, oh well then they're not going to study because they'll get revisions. The way you did it where you can recover, like being upfront, like you can recover a certain percentage, like however many percent of your points through the revision process, I actually think was really helpful. After
Right. Well, that was only because I had expected higher scores, to be honest, and so that's where I was like, let me,
But I also
you
know
know,
that there's a lot of there are a lot of classes that I've had exams on that have like upfront been like you'll have your original exam and then you'll have a review, like you'll have a revision portion as well. And also just what I would say is I do think the test was appropriately timed lengthwise for the class. So yeah, just not putting like 700 questions and
well, it's still when I say there's 50, that's a lot. I get it, but that's also relative. I mean, thankfully there were things that hopefully you would go through a little bit quickly. So, certainly the ones at the end, I probably should have put those to the front. Anyway, point being. But here's the other thing I'm asking. More importantly, my other flip with it. Yes, had I known
yeah.
the potential for having results that weren't what I really wanted to see, or better yet, I felt like it didn't fully reflect your knowledge. I thought that was it. So I I understand that part of it as well. That was me trying to be like, come on, let's, you know,
Yes. And I do appreciate what I appreciated is that you were very honest. Like no one is going to fail because of this midterm.
yep.
And I think that placed a lot of trust in you as our instructor to know that one. Like that took a little pressure off of it. It's
I'm
still
sorry for the, yeah, no, it is.
but I do think you did the best you could with the situation.
Well, I tried. but it does help me. So the nice thing about to me is I get the real time data. It's a different data the exam gives me, right? Like the homework data I'm used to getting, and you know, there's that side of it. But then like, so how do you think when I ask you this on your feet is a different type of data potentially? So I feel like there's value in that different, like it's a different skill set to be able to sort of conceptually organize. But I like it, but at the same time, I hate that I don't like seeing people in distress, and I really don't want. I know we all have to take exams. I think Akyung, you told me like all the stat courses take exams. Sorry, but I was like, yeah, comps, everything. Everybody has to take it. So I have to sort of just like be okay with that. But that's on me. The other thing I was going to mention though is in the absence of the philosophical, what do I do? I think the other part of it that you tend to go for when you don't have evidence to support your psychometric argument or use, I think the flip that I've implicitly done without even thinking is more, okay, so let's make it well defined as to what scores are and mean and how to behave, right? So now when you walked into the test, so even though we can say, yes, once you did the test, how I scored it may be not the right way. There may be needing to be more scores or fewer scores or downweighting items. But I did, you knew sort of the agreement. If you answer this correctly, you get points. If you don't, you don't. There's no magic beyond that, right? And I feel like a clear use case or a clear, like, that's sort of a criterion objective way of looking at it would say, okay, I can't go and justify, I cannot go and believe that all the claims psychometrically are true, but in terms of fairness, at least, there's clarity about its use, right? Something along those lines, whether it's good or bad or otherwise. So I think that's like this is sort of the non-PhD part. We can sit here in the ivory tower and think theta, latent variables and thetas and scales and stuff, but when we have to actually go and do it and we can't gather evidence, this test isn't going anywhere. You're the only class that will ever take this test, right? That happens. So what do you think on that argument for me? What do you think? Does that seem to, like, in the absence of psychometric evidence, clarity is the best we could do? Fair? Seem reasonable?
I was gonna say I feel like you justified it pretty well even from the beginning of the quiz.
Good.
But I do think like I said, test anxiety is a
Oh yeah,
beast.
and that's yet another. That is another thing that gets in the way of what we're saying. Yep.
But also, you did a really good job of scaffolding us to know what materials we needed to look at. You were very clearly like, we're only going to cover materials that I taught you. So like that helped us from our studying. And I think the argument.
Okay, that's good. I'm just trying to. What I'm trying to give you an example of is sort of the practical. Like we can teach, but the practical reality of a lot of measurement situations are sort of take you away from the ideal that we're teaching, which seems somewhat hypocritical. You know that all. And by the way, everything I just mentioned about the test, you could apply to your homework as well too, right? Anything where I'm giving you a score, and I know you're probably sitting there now. Now, those of you who are teaching, who are grading, or whatever, you may never look at your scores again the same, and I'm sorry for that. But that's how I look at them now. Every time I do a score, I'm like, gosh, I really wish I had like an IRT model to help me here, right? Something a little bit more objective, because I know the assumptions I'm making when I'm scoring the test. And I've actually, I probably could take, actually, no, I've given you all your exams back. I didn't write down the item response data, so I don't know who's what. So I'm not going to, but I could have. In my younger years, I think in 2007, I taught a class on linear models, and I did do an IRT model. I had 30 people in the class. So I was like, let's look at your exam scores, and we're going to go item by item. Oh, this item wasn't good. Like I had a negative discrimination. Like, I'm going to throw that item out. And people were like, yeah, whatever, dude. But yeah, I should have done that this time, but
I had a professor do that one time, and all she did was talk crap about people who got the questions wrong. So
I would never do that.
don't do that.
No,
Because students can feel very sad.
no, and that's the thing. I don't want to have anybody. I'm trying to treat every one of you with respect,
Yeah.
regardless of what your knowledge or your score or whatever your answer to question happens to be. So I hope I've been able to do that as well too. But all right, this wasn't supposed to be a referendum on my guilt for giving you an exam. It was more trying to build both together. I'll work on the guilt side. All right. I have nothing to blame for. There are people who blame certain upbringings or religion or whatever. I don't have any of that. I just recognize I don't like to make people stress on account of me, but at the same time that comes with the territory a little bit with this. But all right. Okay, so let's dive into today's topic. Measurement variance or differential item functioning. Measurement and variance we use, it comes out of the psychology, social science world. Differential item functioning came out of educational measurement, right? Measurement and variance, the word invariance is the key there. Invariance in English roughly means but roughly the same. Oh gosh, I shouldn't, right? It's all right. The kids, YouTube can't see my hand motion, but yes, it's a popular child numeric device these days. Yeah, never mind. I'm trying to avoid saying 6 and 7. Measurement and variance, things being the same, right? Differential item function, clearly things being different. So really what we're looking at is two philosophies and where they come at, right? In psychology, this is me just speculating, but in psychology, we'd like to believe our scales are invariant across people, groups. You pick a demographic or otherwise indicator of an individual, and that when we give you a score, it means the same thing regardless of what background you have, what history, or any other salient factor for the exam itself. Same thing, differential item functioning, that is saying basically, we need to be worried about items that behave differently for different types of people, right? But they're both after the same thing. Can we believe the same scores? And if you think back to the original path diagram of the marital happiness, I keep going back to that, right? Where we had the 5 items measuring one trait, and then we had this marital happiness predicting that trait, marital status predicting that trait. For that to be true, let's flip for a second to what we know about this from a path analysis point of view, right? Or I guess this is getting into some causal inference, a directed acyclic graph. I don't know much about the causal inference language for it, but I certainly know graphs and so forth. So actually, give me a second. Let me pull that diagram up. Just a moment. Yes, I know this is dangerous. At my age, I shouldn't do anything impromptu. But this is really, it's getting there. This is what I was talking about, right up here. Okay, so here is our 5 variables. Let's just, for a second here, flip our mind over into path analysis world, where everything that is any shape whatsoever is a variable, all right? It doesn't matter whether it's latent or it's observed, it's just a variable, okay? If that's the case, we have marital happiness, we've got x1 through x3 right here. We say happiness, the happiness latent variable is mediating the relationship between marital happiness and each of the items. That's what we would say. It's a path analysis, sort of in a weird way of looking at it. But what do you think happens if there is a direct effect of marital happiness on each of these items? That's not listed there, right? What if marital happiness affected X1 directly? Or if marital status affected X1 directly, right? What would happen to this diagram potentially? Think about it from a path analysis perspective. In a path analysis perspective, if we have a diagram that really should be between an arrow that should be between these two boxes, that direct effect is likely to change the indirect effect now that we're controlling for it. And the indirect effect is the product of these two values. Now, because this part right here is not affected here, this line right here, this factor loading may change. And if the factor loading changes, what happens to the trait for people? This factor loading changes, the definition, now we got to go back to factor analysis world. If this factor loading is different, right? Or better yet, let me back up for a second. let's envision it a little bit differently here. Yes, I know, the worst part of class. But let's imagine we have marital status. We have happiness as the latent variable. And we have x1 right here. Okay? And what I'm saying is, if this line were actually true, what's changing? Right? So x1 before equaled intercept plus loading times happiness plus error, right? So now when we add this line, we have to add some regression weight times m. I'll call it beta 1, this thing right here, right there. Moreover, so now what you were saying is the factor loading might change. Now, when we put another predictor in, if m and h are correlated, right, then yes, that will change the loading. But let's hold that off for a second here. Literally what's changing when I add that line, though, is the following. Because m is either a 0 or a 1, right? Now, x1 could have two different results, right? For x1, when m equals 0, is mu1 plus lambda 1 h plus error. And when m equals 1, x1 is mu1 plus beta 1 plus lambda 1 h plus error. So now what happens is, if this regression weight beta is not equal to 0, now we've shifted our item intercept. And for some people, our item intercept is mu, and some people it's mu plus beta. It's changed. Now, do you remember a little bit about the item intercept in a factor analysis? Its relationship was with the factor mean, right? Potentially. But let's stop for a second. There may also be something I really can't denote on this, which is the potential for an m by h interaction. Right? And now that m by h interaction, when m equals 0, it doesn't do the same. It basically goes away. But when m equals 1, now what we end up having to replace here is we end up getting a beta 2 times h. And that means all these terms right here can be consolidated into lambda 1 plus beta 2 times h, or the factor itself. So now the interaction is potentially somewhat different. Or sorry, the interaction may be there. If beta 2 is not equal to 0, our interaction now indicates that the factor loading has changed. So that's a big problem, because when the factor loading changes, or if you have one group that has one set of intercepts and factor loadings, and you have another group that has a different set of intercepts and factor loadings, that means the scores on the latent variables will be different unless you control for them, right? Basically. Or putting it another way, people with equal values of h may have a different expected score on the item. Sorry, people with the same value of h will have a different expected score on the item. That's a problem, right? So, yeah.
Is that almost creating like a random variable
So this part right here is a little bit weird. Yeah. From an estimation point of view, the way you do this is a little more complicated. Yeah. But conceptually. Yeah, it's not necessarily random. Depends on your paradigm of estimation, if it's Bayes versus not, but yeah, that's probably not a this time question. But that's just because it's a actually really technical answer that I haven't given you the background for. But this is what we're basically after. What I've described up here, there is a term for it in the more recent literature on differential item functioning or measurement variance, and this is moderated nonlinear factor analysis, and which Lisa likes to call MNIFLA because of the letters. that's the concept. Where it started was very different, and that's what we're going to get into here, right? So there are ways of looking at this from a linear models, almost like analysis of covariance point of view, right? When you get into this equation where H is categorical, H is continuous, a latent variable, and M is 0, 1, or categorical, this is basically analysis of covariance with an interaction. Right? If we could observe, remember back in the beginning of measurement models, it said, imagine you could observe the latent thing that you're trying to measure. If we observed H, this thing is what you did in the end of intermediate statistics here at Iowa, right? Where you had a continuous predictor, a categorical predictor, and perhaps their interaction. Cool. If M is continuous, it fully extends, right? So M might be age or time in study or name a variable, right? If that happens, okay, great. This is the framework where if you have a continuous M, you can test for invariance across the continuum. In this case, it's a linear continuum. You can also do nonlinear. You can do other versions as well. But this idea is a more recent addition to the literature, even though it sort of was the beginning of where we're headed. But when M is categorical, the methods I'm about to show you are built around comparing for group differences on items. So that's what we're going to get into. Any questions? Okay. Now, last thing before I said we're going to get into it. I'll just get into it. So in factor analysis, we can assess measurement invariance, also known as factorial invariance or measurement equivalence. That is CFA term because CFA, remember the history of this factor analysis there came from social sciences. What this concerns is the extent to which the psychometric properties of the observed indicate, so these are the variables that you collected, are transportable or generalizable across group. Think gender, think sex, think countries, think ethnicities, think language, you name it, right? Or by time or experimental conditions. So in other words, we're testing whether the indicators measure the same construct in the same way, right? So not only do they load on the same thing, not only is the factor structure the same, not only is the model fit roughly the same, but do the loadings equal each other across different groups? Because if so, then the indicator responses should only depend on latent trait scores and not on group membership. And that's what this is doing right here. Because if one of these two betas is non-zero, this line applies when your group membership equals 1 versus 0, you don't get those. They're not behaving the same. So what are the ramifications for this, though? So remember in this original design that we have here, what we're effectively doing is looking for mean differences on happiness across marital status, right? So the factor mean happiness for marital status 0 versus the factor mean happiness for marital status 1. If we don't control for differences on the items, those factor means will be biased. That's the problem. And if the factor means are biased, then our whole comparison of group differences are now out the window because now we're group differences on things that really don't represent people of that group. Sort of a crazy collapsing of what we end up having. So to actually do this structural equation model here, which I just said, see, look at that. We just add it together and it becomes a path model. Ta-da, right? There is this step to test for measurement invariance on your latent factor itself. It's needed. Okay. Now, this latter part right here, if you think about this from a educational testing perspective, what if some of the items on my test, were biased against students, let's say in EMS? I only have one student, but just say they are. I don't know what those questions would be, but let's just imagine I did that, right? So that means our one student in EMS would have a smaller percentage chance of answering that item correct than the rest of you, conditional on what you already know. Like if you were all at the same trait level, you have a smaller probability of answering it right. if I were to go and take that item and put it into my sum score, what does that mean about my sum score for you? It's going to go down, but it's going to go down, but not because of what you know, but because now I've given you an item that is hurting you based on who you are, not what you know, not what I'm assessing. Item bias is what I'm going for, right? And you can see an item bias, it changes the sum score, right? If our EMS student is less likely to answer it right, on average, if we keep doing this process again, your sum score will be a little bit lower than everybody else because of that item, effectively, right? So the big picture about why we're concerned about measurement variance from a scientific point of view, let's say if we're studying phenomena like happiness, is we want an accurate version of what the study happens to represent, right? We want to see if happiness is conditional on something we're controlling for, something along those lines, right? Or better yet, we won't get a better estimate, right? But if we're in classroom or educational measurement, we're concerned about this because we're now going to go and give test scores that disadvantage certain people, not having nothing to do with their ability on the test itself. Right? So it's now another validity issue. And actually, that's one I should have added to my list of concerns for you in our test here. Because part of a validity study that you would end up doing is looking at differential item functioning across groups. Gender is a big group. In the K-12 sense, we look at gender a lot. We look at ethnicity. We look at free and reduced lunch status. We look at all sorts of whatever variables we can get our hands on from students. We try to make sure that items are very well protected. So anyway, so in IRT and IFA, it's the flip. So how are we doing on the concept? I know I'm belaboring this point, right? It's going to basically involve analyses to disentangle whether or not each item has a difference in their parameters based on our group variable. So there's two distinct types of invariance. In measurement invariance is going to concern how the indicators of the item measure the latent traits. An invariant measurement model has the same factor loadings, intercepts or thresholds, and residual variances and covariances. Literally, if you look at our model for group 0 and our model for group where m equals 1, our model for group where m equals 0, and this is not the combined model, this is just literally our measurement model, conditional on m being 0 or m being 1, we're looking to see all the parameters of the model are equal across the two groups. Right. Measurement model invariance is a precursor to any group comparison. Right. So number one, we're worried about group comparisons. We got to make sure we have invariance. Number two, if we're worried about looking at valid test scores, we got to have invariance. Right. Now there is such a thing where this is a lot. This is a big ask. Right? You can think about statistically speaking, if we're doing hypothesis tests, null hypothesis significance testing, if we've set up an environment where we're saying, are these equal to each other or are they not, right? There's a nice hypothesis test and we're talking about for every parameter. But you know in your models, we have tons of parameters. So just by chance, it's possible we have one or more of these that might look non-invariant, that might be different. If that's the case, what do? Well, it turns out if we can control for it, if we can allow that parameter to be different, we achieve something called partial measurement invariance, somewhere in the middle, right? Where most parameters are the same, but the parameters that aren't the same, we're now controlling for based on the group variable. Therefore, now that we're controlling for it, we should be able to make that group comparison if we want to. This still doesn't help the educational measurement group, the test bias as much. Because if we said, no, your GRA scores, they would have been biased, but we adjusted them based on your gender. How would you feel about that? Right? Because that's the statistical adjustment we're talking about. So in educational measurement, we don't do that because it threatens the validity of the belief of people's or trust of people. Part of validity is trust in the assessment itself. So what we would do in educational measurement is if we see an item that is exhibiting non-invariance or bias or diff, remove it altogether. Take it out of the assessment. Because otherwise, trust in the assessment isn't there, right? Can you just imagine that? Yeah, these are adjusted GRE scores. We controlled for whether you're a man or a woman. The end. I didn't say which way, right? But Nobody wants that. Nobody wants that, right? So that's measurement invariance, right? Involving measurement model parameters. Measurement model parameters, again, that's the model where the data and the latent trait touch, loadings, thresholds, residual correlations, thresholds, intercepts, excuse me, residual variances. Then there's the factor structure itself. So when you have structural invariance is looking to see whether or not the factor parameters are the same. So whether this factor means, factor variances, factor covariances. Now, measurement invariance is critical. Without measurement invariance, tests of structural invariance are invalid. They depend on measurement invariance or partial invariance because the items are what create the factors. So if the items have biased things going on, you won't be able to really tell on the factors. Or if you can tell, it'd probably just be nonsense that you're getting out of it. So the structural invariance, this is key, but sometimes it's okay, right? Structural invariance is what gives us group differences on a trait. Is there a group difference in happiness for those who are married versus those who aren't? Again, I wish I'm going to change that example next because I'm getting tired of talking about marriage and happiness. I'm just going to, maybe that'll be 49ers fans or not, because that would be better, right? Erica, are you no? Do you have a football team? No. Okay, that's better. You abstained. Fine. I was just going to say the answer is 49ers. I was doing my best not to rip on your hat, but I had to. YouTube, I would like to report in Iowa City a spotting of a Green Bay Packers winter stocking cap with a great yellow GB on it. Yes. That is the wrong hat to wear on test day, but thankfully it's not test day. So you've already passed. Oh, you did? Okay, never mind. I didn't take it out on you, I promise. I know, exactly. It's like I'm going to get the most classic student reviews this time. Mark me down for wearing my Packers hat. Yeah, that's right. So structural invariance, not necessarily a problem, right? Measurement variance, huge problem. Structural invariance just maybe the nature of the thing that you're measuring. Okay? And at that point, I'll just say this one slide and we'll move forward and we'll take our break. If you have independent groups, the way that we test for this is something we call a multiple group model. Now remember that group is the key word there. If M that I showed in my slide over here was categorical, that's a multi-group model. If M is continuous, you're going to have to use these other methods, right? So you can do this in Lavon, you can do this in M+. I'm going to show you how to do this in Lavon. There's pretty much every measurement model piece of software has a way of doing group analysis, diff/measurement variance. If you have longitudinal or repeated measures or so forth, it gets a little more complicated, but you can still do it in the same approach. How's that sound? So I'm going to leave that there, and let's take a break. Pause for 10. I hit record. Hello again, YouTube. You didn't. 10 minutes later. That's what I got to say, right? All right, so this longitudinal thing, what I was trying to say with it is the following. What we will do is think about let's imagine we're measuring happiness over time, right? And we want to compare time 1 happiness and time 2 happiness to see if the items are invariant across time. That would be an important feature to ask. In that case, time 1 happiness is its own latent variable. Time 2 is its own latent variable, right? Items at time 1, items at time 2 are their own indicators. And what I mean by that is this here. Job satisfaction at time 1, job satisfaction at time 2. You may have 2 4-item indicators of it. The items are the same questions, but we denote the responses by the time they're at as well, too. This would be a sort of repeated measures invariance model as well. But really, let's start with the CFA model for measurement measurement invariance testing. Right? This is our CFA model with 2 factors. We will begin with the idea that we'll use standardized factor to identify this, meaning the mean of each of these factors will be 0, the variance will be 1. You can see each of the parameters. There's 3 items that measure each factor. So there's 3 loadings, 3 unique variances, 3 intercepts down here. You've got potentially a factor covariance or correlation as they're standardized, right? For each of these, right? So So step number 1, or step number 0, somewhat optional. People don't usually do this, I would say. So why it says optional. Optional in some senses. You kind of like this information, but it's also, I think the debate is whether or not it's somewhat overpowered, somewhat more, it'll lead you more thinking there's bigger problems than you might have. But basically, what you're after is, if you remember in our factor model, most of these parameters, particularly the loadings and the unique variances, and then of course the factor covariance, they related to the covariance matrix. So an easy way of checking whether everything's all equal all at once is to compare two covariance matrices, right? So that's what this omnibus test does, right? Do the covariance matrices differ of the covariance matrices of the items? Well, we can do this if they do differ. Let's put it this way: why it's optional. I misspoke of just a moment ago. Another mistake. It's not power. It's just this is an omnibus test, right? We know from this model, when we look at the covariance matrix, we're wrapping in all 6 loadings, all 6 unique variances, and this factor covariance and the factor variances being 1 and equal to each other, right? So we're wrapping in all those parameters. So what we do is we're saying all those are embedded in the covariance matrix for each. So if I do a hypothesis test where I say the null hypothesis covariance for group 1, covariance for group 2 are equal, the whole matrix, that's a synonymous hypothesis. We're saying with all those measurement model parameters that are in those covariances are also simultaneously equal. It has to be. So if you do this test and you see there's no difference between groups for the covariance matrices, you've pretty much finished your work. You're all done. Hooray, right? Many people disagree about doing this in the first place. Why might that be? I'll just say it. Because it doesn't give you the nuance of which parameters and how different they happen to be. There's no effect size, right? So you may get statistical significance. Is it practical significance, right? It's hard to quantify. It's hard to quantify for each. So really what we get to when we start step 1 is the process of looking at each set of parameters and testing for invariance, going sequentially, right? So, but we could do this, and so let's proceed with an example. Or as we go through the slides here, and then when we get done with the slides, we'll get to the example in the next hour. We will begin with an example with those 2 factors right here, 6 indicators or observed variables. And then they have 3 indicators per factor, which we will call simple structure. And we'll look at it across 2 groups, okay? So when we do that, if we look at the total number of possible parameters, that's the covariance matrix. The covariance, if we have lowercase v, I think that's a v, or is that, yeah, that's a v, or is it a new? Anyway, v, if we have v variables, then there's v by v covariance matrix. The total number of unique elements is v plus 1 over 2, right? So there's 27 different variances, and that's the covariance elements. These are the means right here as well. And then our combined degrees of freedom possible would then be 2 times that, right? 27 per group, so 57 overall. But when we get to step 1, the first thing we talk about with step 1 is called the configural test of configural invariance. Configural, what do you think the word configural means in English? Anybody use that? Okay, configure can be changed. So if I said the configuration, setup, okay. Okay, now we're on to it. This is testing whether or not in each group the items load onto the same factor. Is the factor loading pattern matrix the same across groups, right? So it's basically what we're asking here, do the groups have the same setup, the same configuration, the configural model, right? So same number of factors, same pattern of free versus 0 loadings. So what are we doing there, right? So if we did an exploratory factor analysis within each group, which we're not going to do, but if we did that, what we'd want to see, we would say, oh, look, here's some big loadings, here's some not. For us, what we're thinking about is if we separate the data into the two groups and we ran just the model within each group, does that model fit in each group? That's really what we're after here. Because if that same model fits in each group without having to modify it, we pass this test, right? Then, so basically what we can do is we can test basically running these different models, but allowing all estimated parameters to differ across groups. Almost like saying within group one, what's the factor structure? Does my model fit? Within group two, does my model fit? So herein lies the problem with configural invariance. What happens if in group one, in our example, it fits the way we expect, but in group two, we need a residual covariance between items one and two? What's that? It's not the same, right? If we needed this residual covariance, let's say between item one and two. Well, when we get down the path of invariance, we could make them the same if in group one we added a covariance and we just let it be 0. Now the covariance parameters are different, so we might have something that's called residual invariance, but we achieve configural invariance by structuring the model that way. So what I'm getting to is one way of what people will see people getting configural invariance is going through each group and coming up with the changes for each the model they would have to make, and then compiling those into one big model so that they're represented across all groups, right? Again, for group one, if I fit this model and it fit, that's great. But I get to group two and I say, oh, I really need this residual covariance. Well, I can go back to group one and add a residual covariance there. It will still fit just as well. That covariance would be 0, right? So now I have a model that is the same across groups, even if it wasn't the one I started with. But do you see where I'm going with this? Like, to get to configural invariance, you really have to have, you have to sort of work your way through the groups to make sure the models are the same, and that big model, the one that sort of includes all the additional parameters, can be mapped onto each of the groups. Does that make sense?
Struggling with the idea of when we were talking about factors and adding residual covariances and that undermining our argument about
Oh yeah.
So I'm sitting here like, I don't think we're supposed to do that anyways.
I agree. No.
Your argument you're making is truly just a way to make the models equal.
Yes.
Not at all about whether or not it's right that we do that.
Correct. And actually, what you would say, the other flip to that is, they're not measuring the same construct, so therefore.
Exactly. That's what I'm like, okay, so, but if I have a residual covariance there, I'm already throwing my model out. Like,
Potentially. Yeah, you're basically done already. You're saying they're basically doing it different. Now let's say, okay, so, but exactly, right? You don't want to have the residual covariance in a measurement model in the first place.
yeah, okay.
But that's another example. Another example could be, okay, so imagine I need 3 factors in one group and 2 in another, right? Maybe not with these data. 1 factor in one group and 2 with another. Can you map that onto one where you don't do the harm? It's not as easy, right? So, but the fix to it, what I'm trying to say is one of the fixes you will see is people adding those to say, yes, they're not the same, but let's adding the residual covariance saying, okay, so I'm just going to weaken my factor argument slightly, but controlling for it now, whatever this other factor is, I've sort of controlled for it so I don't have to worry about it.
That makes sense. Thank you.
Thanks. Yeah, it's a tough one. All right. So turns out this also is an important test as well, because when you estimate the configural model and all the parameters are different across groups, you can't get any more general than that. You're basically starting with the most parameters that are possible, right? Because every group has its own set of parameters and its own model. They don't talk to each other. They're not on the same scale. They may not mean the same thing. But that's the worst it gets, but that's also the most number of parameters. So in every step we go on from here, we're going to go and build an analysis that where the groups come together but certain parameters are set to be equal across groups as we sequentially build our factor model. Okay? So the configure model, it's critically important, first of all, just to say whether the structure of the trait is the same across groups. But it's also important because it serves as a baseline for the comparison. This now becomes, remember in our model fit statistics, the saturated model is H1. This is our saturated model across groups, the configural model. That is the biggest, right? So that means this fit will be the best. It can only get worse from here. Why do I mean that? Because good fit usually comes from more parameters, and we can't get any more parameters than this one in this class of models, right? How are we doing? Okay. So this is an example of configural invariance. If, for instance, group A looks like this, but group B changes the direction, that's bad, right? That means you don't have the same construct across groups. So you can stop. There is no group comparisons. If you were to compare, let's say, imagine our study was designed to get and see if these two factors differed across groups. And then you go into configural invariance, and one group structure looks like this, and one group structure looks like that. Now these factors aren't the same thing. You've got the apples and you've got the oranges. So does it make sense to say, oh, group one is higher on apples than group two is on oranges? Probably not, right? That's what's going to happen. So if you get in this spot, you could just be like, groups are different. Most uninteresting finding in the world. I can't give you any nuance, but yeah, can't compare. The workaround, as I was mentioning here, is fit two. Actually, yeah, this is. I'm sorry. I'll just skip through this. But all right. So what we're going to be doing is testing whether removing parameters by setting them equal across groups worsens our model fit using the likelihood ratio test. Right? So think of it this way. We're going to do a step coming up here looking at just factor loadings. Right? Now there's one little caveat we have to add to be able to do that. But when we do that, the null hypothesis is all the loadings are equal. The alternative is they're not equal. Right? So now we have a nested model situation. We can get a log likelihood from the model where they're unequal. That's our configural model. Compare a model where they are equal. Do a likelihood ratio test. And now we're testing all the loadings at once. Right? So in the slides, when we say removing parameters, what we really mean is equating them across groups. Because in our example here, we have 6 loadings. Across the 2 groups, we'd have 12. So the configural model would have 12 loadings. But when we test the loadings, that constrained loadings would only go down to 6. So they're removed in some ways. The uniqueness of them are removed, but they're set to be equal across the groups. Does that make sense? Now, if you're doing MLR, the robust maximum likelihood, and M+, you have to do a little bit, you have to sort of build things. But if you're in Laban, the ANOVA function in R will work. You don't have to do anything else. So that's a good thing about R. Good. So what happens if you're removing, right? If you're equating parameters, the null model, the one where the parameters are equated, can only get worse. It basically can only get worse in fit, right? So we're testing whether or not equating all the loadings makes the fit any worse at all. Does it any worse or not worse? Right. All right, so this is the scaling factor. You can avoid that. So our configural invariance model looks like this. Every one of the, so now if you look at each of the items, each of the subscripts represent not only item number, but group number, right? So items 1 through 6 are here for group 1. So item number is the first subscript of Y, group number is the second, and then group 2's items here. Now they're the same items, but we're going to treat them differently for each groups as we look at the equations for it. So the equations are kind of our guidepost. This model, the configural model, all the parameters are different, So you'll see each parameter has two subscripts too. Mu11 that represents the item intercept for item 1, group 1, whereas mu12 is the item intercept for item 1, group 2, and so forth for the intercepts, so forth for the factor loadings. And you can't see them on here, but each one of these error terms has a variance that goes with it. And each one of those would also have two subscripts, one for the item and one for the group. Right? So in the measurement model, for a factor analysis, there are three sets of parameters: intercepts, loadings, residual variances. If you're in IRT world, all of this still applies. Still use Levon. You just don't have the residual variances to work with anymore. Right? They have other things that we don't usually talk about. All right, so here's what we can tell. All right. The model degrees of freedom. Actually, let's see this here. All right, so the first test that we're going to forget the great degrees of freedom here. Let's just go through this. For the test of metric invariance here, sometimes we call this weak factorial invariance, right? The question that we're asking is, do the groups have the same factor loadings? It's an important question, right? So now from step 0, we established the pattern of the loadings onto the factors are the same, meaning the same items measure the same thing. This is asking, is the strength of that relationship equal across groups between item and factor? So each indicator is still allowed to have a different loading within each group, right? Loadings for the same indicator are constrained. I'm sorry, saying this badly. What we're going to do with this is basically take the subscripts off the loadings. Okay? The second subscript. Right? The first subscript, each item will have a different loading. But now we're going to say loading 1,1 is equal to loading 1,2. Right? Or loading 2,1 is equal to loading 2,2. And what we'll end up with, if we could basically drop the group subscript from that loading because it's equal across groups. Okay? That is what this is trying to say here. The other thing we have to do is because what we'll have to estimate the newly constrained factor loadings, and we can fix the all the factor variances to 1 in the reference group. So let's imagine group 1 is our reference group. So our factor variance may be 1, and our factor mean may be 0. Right? But in the not reference group, we actually have to free the factor variance. Why is that? Would you think? It's a tough one. So remember, the factor loadings are what the factor variance would be derived from, in part, from when we go to a marker item. Let's think of the differences between marker item and standardized factor, but not in a multi-group sense, just a regular measurement model, right? When we used a marker item, we were able to estimate that factor variance. And the factor variance came from the item, sort of a part of the variance, the item where the marker was placed, where the factor loading was set to 1. So if the first item had a loading of 1, the factor variance was a portion of item 1's variance. Well, for our case, what that really indicates is the factor variance is related to the loadings. And if we set the factor variances to be equal, that's a strong assumption about the structural portion of our model. But we don't have to make it, because what we can do, the model happens to be identified if we basically equate all these loadings to be the same. That one basic within factor, remember the first 3 items measure a factor. If we were to look at marker items, again, not a measurement model, we'd need to turn one of these, put a constraint on one of them, right? Well, between the 2 groups now, we actually have 6 constraints. So we satisfy the need for the constraint by the multiple group approach. And so because of that, in the second group, we're going to allow that factor variance to be estimated. Actually, I should get to this part right here. This slide, right? So now all the loadings are set to be equal, in the reference group, we standardize the factor, right? So mean 0, variance 1. In the group where we're testing, sometimes called the focal group, we allow the factor variances to be estimated because that we can, and it allows us to remove a critical assumption from what we're doing. But the means are still set to 0. And the means are 0 because the means, we know, the factor means are implicated in the intercepts. So that shouldn't affect us in this analysis. Do you understand where I'm going? So step 2, metric invariance model, is to equate all the loadings, but then for each group but one, estimate each factor variance. Okay? So now when we do that, that changes our model degrees of freedom. We have fewer parameters that we're estimating, right? We went from, we just dropped down here. Instead of having 12 loadings, we now have 6, right? But we do have 2 factor variances that we're estimating here. Right? So what we'll then do is a log likelihood ratio test. Compare the log likelihoods of both. And MLR will be rescaled. And basically, if the fit is not worse, right? Again, the null hypothesis is that each of these loadings is equal. The alternative hypothesis turns out to be each of the loadings are unequal, right? So now you can compare the 2 models, and if it gets worse, we will reject. So if we reject the null hypothesis, we're saying at least one of those loadings is unequal across groups. Now the fun begins. Exactly. We just did the omnibus test, as you remember the NOVA language, which, again, only in a NOVA and like politics, omnibus shows up, right? But maybe there's other places. Maybe public health has omnibus chemistry. I don't know. Anyway, that's where I'm thinking of it. How do we test? Well, it turns out in the metric invariance model, we made those constraints, those factor loadings are all equal. So what we can do is look at modification indices. No, we can just look at our mod. Yeah. And we can tell which one of those loadings had the highest modification index, make those parameter estimates. So let's imagine we do this and we see, loading 3 had the highest. What we'll go back to is you go back to your metric model and you just allow loading 3 to be unequal across items. Right? If it's unequal across items, then you end up with partial measurement invariance, which is where you want to be. Okay? How are we doing? Yeah.
For the modification index, we still want it to be greater than 3.84. If I remember correctly, to say that it's worth changing.
There's debate. Yes. And part of it is we're making to test whether loadings are significant or not is very absolute. We have no measure of effect size that we're using. And so really, there have been numerous papers in ink printed or displayed on computer screens, probably more appropriate these days, to show different ways of doing this. I'm just staying with the hypothesis testing. Every other way, you have to sort of make a criterion as to where your cutoff might be. And that criterion is not as identifiable, but still the same process, yes. Yeah, one easy way to make a criterion for it is to say, I need a lot of evidence in my modification index. That's sort of something that happens, right? But
Field and even like
probably, yes. And it changes by reviewers within field. So it's hard to give you, there's safety in hypothesis testing, but there's also danger, right? You might say things are different when they're trivially different. Well, I guess that's not that dangerous because what you're doing is sort of allowing them to be different. But yes. Okay. So if you don't have partial measurement, if they're all not equal, if all the items on each factor are unequal, or one or more loading per factor is partial invariance, where they're the same. But if they're not, you can stop. The traits don't measure the same thing in each group, or don't do you don't have, there's no way of looking at group different. You can't basically go on, right? Okay, so the next step. We move from loadings to item intercepts. I can never remember the names of these things. Some people call this scalar invariance. Some people call this strong factorial invariance. I just want to call it invariance of intercepts because that's exactly what it is. I don't need these English words putting feelings like strong. Like what makes this so strong, really? Like thinking like my kid saying, "Oh, it's one of my characters that's buffed, right? Like got muscles and stuff." But it's the verb buffed. He got buffed. Anyway, so this is testing item intercepts. Each indicator is still allowed to have a different intercept. So item 1, 2, 3, 4, 5, 6 are different from each other, but their intercepts are now equal across groups, right? Or put a different way, each one of these, mu1 through mu6, is the same for each group, but each item has a different intercept. We're not constraining across item, right? So you need to have scalar invariance for factor mean comparisons. So what I mean by that is, if you end up saying item 3 I needed to change, you would just leave it out of the next set of comparisons. You'd say item 3, because I needed to add its loading, I'm just not even going to test for invariance. It's just not invariant, right? So item 3, I'm just going to acknowledge item 3 is not invariant. Take it out of the group. So that's the other part. And then finally, just like with the loadings, the item intercepts are related to the factor mean. So previously, in our last step, we had to go and free the factor variances across groups, the non-reference group. Here, we're going to free the factor means and estimate those in the non-reference group. Okay? For the same reason, because that's an unnecessary constraint that may distort our findings. Okay? All right, so here we have it. Now what are we changing? Well, now we have 6 means instead of 12, or intercepts. We have 2 factor means instead of 0. So there we have it. And here are some of the implications of non-invariance, right? So if you were to plot the item score by the factor score, this is what you would end up getting. If you have achieved metric and scalar invariance, then the item response function, right? The expected score on the item, conditional on the latent trait, are roughly the same, right? They should be right on top of each other if they're exactly equal. This is within some type of error tolerance, right? Okay. If you have metric invariance but not scalar, metric being factor loadings, scalar being item intercepts, what you end up getting are parallel lines, right? Remember, the loadings are the same, so the slopes are the same, but the intercepts differ. So what this would tell you is for a person who's at the dashed line on the latent factor, if you were in group 2, you would rate the item much lower than if you were on group 1, right? And if these were not the actual item, but these were logits, this is what would be an item response theory as well, right? Now you're talking about an item response characteristic curve that gives you a lower chance of answering the item right. And so again, you can see each different permutation. This looks like a whole lot like ANCOVA, doesn't it? From linear models, it's analysis of covariance across groups. Okay, questions on any of that? Well, this is the test of hypothesis. And again, you still need partial scalar invariance to move forward. Now we need to move on. We're going to, yes, question.
So if you remove the factor and it's going with one item, do you need to go back and make sure that everything is still equivalent with everything else, or is it
By removing, what I'm saying is not remove it from the analysis, but allow it to have different parameters across groups.
but we aren't worried if that one is changing?
Correct. Because it's still there and it's still the same. So for instance, item 3, if I said, oh, we need to have separate loadings, both of these would be different, and then we wouldn't even constrain the intercepts for item 3 to be equal.
Okay, so we're not changing what we're measuring.
Right.
Yeah, got it. Okay. I thought we were completely.
Oh yeah, no, we and that's the thing. If we take that item out, then all of our analyses have to be redone because then we're in the likelihood ratio test wouldn't be the same after that, right? Thank you for asking. Other questions? Okay, so now once we're done with the intercepts, let's move to the residual or error variances, unique variances, right? And again, this is called strict. I can't remember strict. There's some debate as to how much this affects your results overall, whether it does at all. So you will see some people not talk a whole lot about it or worry a whole lot about it. They allow errors to be different. It's our last step of measurement invariance. Right? And again, indicators, items that didn't quite get through scalar or metric don't get tested, although they could be. Equal error variances is often misinterpreted to mean equal reliabilities, but that's not always the case because reliabilities also involve factor variances across groups as well. Right? And actually, they also involve factor loadings, as we saw before as well, depending on which measure of reliability you end up having. But the error variance model, now in the slides, error does not have its unique variance denoted, but you can just pretend it's fixed here by that. We constrain the unique variance or error variances to be equal. We don't make any other constraints to the factor part. Right? And we test and we see. So this is very repetitive, right? We test first we do the loadings, then we do the intercepts, then we do the unique or error variances. Same process over and over and over again. It's tedious, but it does do the job. But finally, we get to the part where this is our most important part. For instance, this is the test of structural invariance. Another way of putting that is almost the same. It's not exactly because of one difference in parameter. But remember that first model, that slide I keep going back to. Right? This MRR variable is dummy coded. It's 0, 1. So it has the groups indicated. So this coefficient that's on it is literally a difference. And it's a difference in group means. So this in and of itself is like a test of the factor means across groups. But to do a proper test in the path model, the way I specified it, if I didn't do anything differently to my code, then the unique variance of happiness would be equal across groups. And typically in the invariance analysis, we test for unequal unique variance or residual variance as well too. But that's what this next test is. So when you get to this part, that slide I gave you before, we actually get a better answer to this question from the test of structural invariance when we have a two-group variable, because we're allowing for different factor variances across group as well too. In the linear model sense, whenever you're predicting not just the mean, but you're predicting the variance, there's a term for that. It's called location and scale model. Lisa knows those because of the random effects versions of location and scale models. We're saying effectively, I take my linear model and I take a function of the variance, like the log of the variance, and I predict it with a set of predictors as well. That's what's happening here. Basically, we're taking a function of the variance and predicting it, the group variable. But here's what we're trying to do. We're testing whether the factor variances are the same. Right? The factor covariance, are they the same? Factor means are the same. Same thing would happen, right? For each one of these steps, we could go and test by adding parameters, right? I personally would go through this. People do it a little bit differently throughout. I tend to just allow everything to be unequal versus everything being equal, because it doesn't make a difference to me. I mean, I'm more usually interested in mean differences. But I want variances and covariances to be different, because that would be the difference of, this is what we call homoscedastic residual variance. Just rolls right off the tongue. I mean, I've been doing this a while, right? Constant unique variance is what's happening here. But this is non-constant unique variance. This allows it to be heterogeneous. So it's a little bit more general of a test, that's what I'm saying. How are we doing? Doing okay? So I'm going to wrap up these slides. We'll take a break and I'll start showing you the example. But in CFA, invariance has two distinct parts, measurement variance and structural variance. Measurement variance is testing the item and the items themselves. Is your construct being measured the same way by the same indicators across groups or across time? And then structural invariance are do the factor means and variances differ across groups? Right? In item factor analysis, we still call this testing invariance. It's pretty much conducted this similarly. The statistics behind the hood are a little bit different from how they're calculated, going from categorical data to continuous data to categorical data. Now, in item response theory, the practice that we're doing is called differential, goes into the heading differential item functioning. But the history of item response theory is a bit different. So if you take an item response theory class and they talk about diff, they do it a little bit differently. In fact, there was a great paper some of my grad school colleagues wrote in 2006, sort of comparing the two different fields. And what I interpreted their decision to be is the process of measurement variance here really is much more robust than statistical assumptions that you're making throughout. Not all, but most methods in item response theory that have come out of educational measurement, most likely, started with, yes, I see the smile, started with the idea that the traits were the same. So for instance, a very classic statistic for this that you see, not even item response theory based, sort of applies under the Roche model, but something called Mantel-Hansel. It's an actual a categorical data analysis statistics that came from the statistics, the field of statistics, like here in Schaefer Hall from the 1960s, right? And what it does is it conditions on the total score. And it says, are there group differences on items across the same levels of the total score, right? Well, to do that, now you have to condition on total score, which assumes everything is invariant. And the paper that I'm referencing sort of showed that if you assume everything's invariant, guess what? Everything looks like it's invariant. You're less likely to find group differences. So when I look at the two fields, look, I do most of my work, my research, my practice in educational measurement, but I got most of my training in psychology or in statistics and broader than just a little bit in educational measurement too. This is one of the weird differences between fields because even like if you look in test manuals of published tests, you'll see statistics that are far out of date. Like a long time ago, ETS created a scale trying to note how much how much bias there was in items based on some of these statistics and levels, like almost like effect size, which is a good idea, effect size. People still do the same method, the same scale years later, even though we know the flaws statistically in each of these tests. So when you hear this, you'll see it. Now, the item response theory, I'm going to go a little bit into that. I'm not going to go into the deep. Why I say that is if you go in like, I want to do a diff study, that's what I call it, a diff study. I want to go and study differential item functioning. You're going to see a ton of different methods out there. And they're going to be a little bit different than what we see here. So I personally, why I'm focusing on this method, the measurement and variance methods, I find it to be the best from a statistical point of view, right? Where we don't have to make assumptions that of non-invariance go and test non-invariance. I'm sorry, we have to make assumptions of invariance in the process of testing non-invariance, right? That's the problem. But here's how it works in IRT. There's a couple other labels that go with it, so I'll tell you the labels and then we'll be ready for the example. So in an IRT model with an A parameter being our discrimination and a B parameter being difficulty, remember B is the point on the theta scale, the ability scale or the latent variable scale where there's a 50-50 chance of a 1 on the item, right? Measurement non-invariance is the bad thing, or diff, differential item functioning. Diff is bad. Friends don't let friends diff. That's not good either. I'll workshop it. I'll come back. You don't come here for your IRT-related humor, right? God help you. So an item has diff when people with equal trade amounts, but from different groups, have different probabilities of a 1 on their response. So like I said before, if you take the GRE, you don't want to have diff on an item because women will have a different probability. Take everybody who's at the average GRE score. Women will have a different probability than men on some of those items. That would be bad. Bad for a lot of reasons, regardless of which direction, right? Non-diff is the same. Non-diff is the opposite, excuse me. Non-diff is good. You want non-diff items, right? Diff can be examined across groups over time. Same thing as you would in CFA, like I just showed you. Be wary of any approach that involves using outputted scores. And that's what I was just mentioning before. So the methods that you'll see here, output a latent variable that was formed with perfectly equal group parameters. So now there are two types of diff that are described in item response theory. One is called uniform and one is called non-uniform. Uniform diff is diff in the difficulty parameter. Non-uniform is diff, diff in the intercept parameter. Let me go back to diff in the difficulty parameter. I don't want to say diff in the difficulty parameter, but here I am. Non-invariance of the B, diff in the B parameter, means you're shifting where the 50-50 point is. So it's like you take your ogive curve and it's parallel line, right? That's why it's called uniform. The whole curve moves across uniformly, right? Non-uniform diff is non-invariance in the A and possibly B parameter, right? And I'll show you a plot of this. Yeah.
Can you just remind me, metric refers to loadings and scalar factor loadings and scalars the factor means, correct?
Item intercepts. Yep. Okay, uniform diff, uniform diff, same lines. Here, the next slides, for whatever reason, the image disappeared and I couldn't get it. So I'm going to draw it. But uniform diff looks like this. Well, I don't care. You don't have to see it. Yes.
It is still on the slides, so if folks have the slides up, we can always.
Oh, you can see it?
Yeah,
I can't see it. That's amazing because I couldn't see it in PowerPoint. You know what? But here, let's see if I can draw it the same. Uniform diff. So this is our latent trait. This is the probability x equals 1 conditional our latent trait. We might have an item characteristic curve that looks like this. And we might have a different groups. Do I dare try this? A different groups that looks like that, right? So they're parallel, right? And that's because the 50-50 point changed. The B parameter, remember, is right where the 0.5 probability is. So this is the B for each of those. So it's different Bs. Non-uniform diff. Let's see if I can do the same thing. Might have one item that looks like this. You might have another item that looks like that. Right? So now the slopes change. And now the non-uniform diff, the neat case with it, where we talk about it being different, is that if you note right here, that's not 50-50. The lines cross. What's that mean? That means this is the point of theta, the point of the latent variable scale, where one group has one item higher and the other group has one item lower, but then it inverts. So for anybody in one group below this point, they have a higher chance. But once you get above that point in theta, you have a lower chance of answering the item right. So it's this weird combination of values. So non-uniform diff, if you have this crossover point at a certain place, if you were to go and look up items and just sum the item responses, you sort of get a canceling of the diff a little bit, right? Because on average, between your two groups, the overall, if you were to integrate across this or take an average of all the values, you might end up with the same item difficulty, the same proportion correct across groups, but this tells a much more complicated story. And you don't want this to happen. So another reason why we're doing a process that breaks this down to the item parameter level is that certain other processes that we had done before may be susceptible to non-uniform diff canceling diff out. It's sort of a canceling process, right? And finally, the other thing is there are no error variances, right? They're binary items. There's only one parameter, the probability, right? So those are the graphs. I don't know why they're not in PowerPoint, but evidently they're in the PDF. Hey, great. Let's see what else I want to add here. Same process still holds, by the way. There we go. All right, last slide on this, and then we'll get to the example. What if I don't have discrete groups? That's the moderated nonlinear factor analysis I was just telling I started the lecture with. Again, Manolfa? I don't know. Basically, the idea being your item is basically testing this in like an ANCOVA approach. It is a little bit harder to do in certain places, in certain software packages because of the estimation that it requires. It's actually not harder to do in Bayesian estimation. So if you ever take a Bayes, that's right, Erica knows. Right, whenever you take a Bayes class, that's how you do it. But it works much better that way. And none of you are going to take Bayes, right? You promise? Just kidding. I say that because I teach the Bayes classes, or I used to. Not anymore. I hope so. All right, let's take a 10-minute break, and we will resume the fun with the example when we come back, okay? Pausing the conversation. I was going to start with one other thing I didn't mention. I really hate that this is here. They can't change it, so. Yeah, hate math. Anyway, let's imagine I was trying to measure math ability with a 5-item test of math. But better yet, so this is 5. Let's imagine they're like 5-word problems. So my daughter is a freshman at Baylor, and she said her Calc 2 test, like the professor has 5 basically problems per midterm, and it's one of those hard ones, right? So it's going to take a lot of work. So 5 is too long, let's say the person says. So they say, no. I'm going to make 2 forms. I'm now going to make a Form A and a Form B. Form A has items 1, 2, and 3. And Form B has items 3, 4, and 5. So I have 2 forms measuring the same construct. Right? So each student in the class will either have Form A or Form B. I'm going to take their scores on each. I'm going to do my class stuff. Well, this situation happens all the time in a lot of testing programs where there's different forms. And the items that are common across forms have a name. They're called anchor items. I don't know if you've heard those before, but they basically anchor the scale. They're thought to be fairly well behaved. There's sometimes, if you're creating new forms, there may be older items that have been field tested that you know how it works. So item 3 is our anchor item. Well, it turns out if we really want to compare scores from students who took Form A to scores from students who took Form B, we need to understand if item 3 has any measurement invariance. And so now we have an issue where we need to do measurement invariance or diff when we just have forms that might be different. So think about what the data might look for that, right? So here, our data matrix might look like this. Here's our items, and here's the subjects or students, right? So people who took Form A would have responses for items 1, 2, and 3, and there's the dashed line and nothing over here. And people who took Form B would have responses for items 3, 4, and 5, and nothing over there.
That's an unhappy matrix in our world.
It is, but we can still use it. What we won't be able to do is directly get a correlation between anything. So we can get a correlation. So because item 3 appears in data with items 1 and 2, we can get the correlation amongst these 3. We can get a correlation amongst these 3, but we can't get any correlation between item 2 and item 4. or item 2 and item 5. We can't also do the same for item 1 and item 2 with the other two, right? So those where you see zeros there, you can think of that as a correlation matrix. We just can't estimate it. We never saw X and Y together. We'd have to do some weird trick to data if we even want to try to come up with something that's close. But that's our setup. And now we can do it in the variance analysis, right? But we would only do it in the variance analysis on item 3 because everything else is set up to be where there's no way we can test item 1 and 2 for group 2. There's no way we can test items 4 and 5 either. So this is an important step where you see invariance testing as well. Form differences. Do we have differences in anchor items across forms? That would be very bad if we did. Because if we can't link the two forms together, your score from one is not the same, is not comparable, is on the same metric as the score for the other.
So that would have to mean to not be able to equate them at all if the anchor item had that issue.
That would be the hard part, yeah. And then what you'll end up seeing is, so this actually brings up, you brought a good point, the word equating. How many of you heard the word equating before? Equating is where we try to make two forms have the same distribution of scores effectively, right? Sometimes linking. There's a difference when there's a class that Wan Chan Lee teaches on it. I haven't taken it. I'm not an expert in it, but I will say this. The bigger picture is we're trying to take form B and map it onto form A somehow. We would like to have some anchor items that sort of behave the same within it. Equating methods come in all different ways. What Wan Chan would call a linking method is where we just estimate. We could estimate this model. If we allowed for the parameters of item 3 to be the same across groups, this is just a straight IRT model. We could estimate it. And the scores, because item 3 has the same parameters across groups, the scores from each form would then be linked onto a common metric, by item 3 being the thing that sort of pulls the two together. That's fine. That is what we call concurrent calibration as a method of linking. Right? We estimate both the same. Now, there's a whole bunch of ways of doing that when you don't have concurrent calibration. I'm not talking about those. Yep. I like the concurrent calibration approach myself. But then what you can see under concurrent calibration is what basically we fit the model assuming everything is invariant. But we need to go and test for it throughout, is what I'm getting to. So if you got different forms, you might want to do measurement and variance. That's a difference is when you compare, like Lisa had described, her slides had described job satisfaction over time, the same construct with the same items, but at 2 time points. What this is the same constructs with a non-overlapping set of items at the same time. So another place where we may have to go and compare, right? So another way of looking at it. Questions about anything I've discussed up to this point? No questions. Or if you do, just throw them out. Let's get into the example. This is an example where we have data from Brown's Chapter 7 on 345 men and women, rating 9 different items on a scale of 0 to 8. This is a 9-point Likert scale. So if you think about an IRT model I'd run for this, I would probably have 8 thresholds. 8 thresholds would be very difficult to estimate with 345 people when you consider that those thresholds represent sort of discrete points between proportions of people answering in each. So if you end up getting an item where, I don't know, one of the groups has very few people who answered with option 3, which is likely, it won't work. Right? So we're going to treat this as a factor analysis. That's what I'm going with. I know. It's not good. And it makes me feel weak for my own slide, my own preparation to do this, but we're going to treat this as CFA. Okay? There. It's me making a joke saying, it doesn't meet my own standard, but I'll just do it anyway. For the didactic exercise. Okay, so in Laban, you already know how to make parameters constrained to be equal, or to label them. Remember this in the indirect effects that you had to create before. You labeled slopes of parameters, and then you made another equation with a colon equals and put those labels in. Well, that labeling process is what we do in Laban, but now there's labels per group. So here, if you think about what we have, we're going to develop a depression factor on these 9 items. So I put an equal tilde in the syntax. And the label for each uses the R notation C in parentheses. Remember, an R that's sort of a deep, it's concatenated. It just builds, it puts whatever the variable in the first, before the first comma and the last comma, and just glues them into one longer string. But that's the notation Lavon chose for denoting which parameters each. So what you have to think about this is within parentheses, you have to know how many groups you have. I have 2, male, female. And so I'm going to label each L1F for loadings that would be for the female group, and L1M for loadings that would be for the male group. So I know that I have 2 labels for the first loading. So it turns out why I'm doing it this way is when we get to the next step and we don't need to separate by group, I'm just going to take the F off and the M off. And when the labels are the same within the C in each of the spots, they're now equivalent. But when they're different, they end up being different values. Am I making sense? I'll show you in just a bit. Think of it this way. This is our way of saying, because there's 2 different labels, 2 different character strings on either side of the comma, there will be 2 different loadings for item 1. Okay? Yeah.
How does Lavon know how which one gets which spots from here?
We're going to get to that. We're going to get to that. Here in Lavon, we have group equals sex. So we actually, when we submit the model to Lavon, we have to tell it what our grouping variable is. So I do that. And then in the model itself, I'd have to know the order. So I relabeled these in alphabetical order because the very first, it goes in basically alphabetical, numeric alphabet, like the combination of number and alphabet there. Technically, I don't think a label can start with a number, so it has to be alphabetical, but yes. Does that make sense? Okay. So, in the configural model, all loadings, intercepts, and residual variances are equal. I mean, unequal. They're all estimated. It's a parameter free-for-all. And I'm creating the configural model where they're done jointly. I mentioned before the concept of the configural model is if we separate our data and we just run the same model on male versus female and look at the results, that's fine. We could do it that way, but it doesn't help us in our next step where we got to do a likelihood ratio test. I'm just building it all to be in one analysis where each of the parameters are different by groups. It should be equivalent to separating the 2 models out. Okay, so the loadings we know come after the equal tilde. The intercepts come after the tilde and are represented by a 1. Right? So that 1 is where we put the comment over. This is like commenting or putting a comment on the intercept in the path analysis. I don't know that we did that, but you could. And then the residual variances, those are denoted by a tilde, right? Double tilde, excuse me, where the item shows up on either side, and now the comment shows up just in front of the item on the right-hand side. Right? So what this is doing is saying, estimate a different parameter for the residual variance for item 1, right there. How's it going? Okay? Understandable? Now, we still have to label all of the other parameters in our structural model. The structural model, and actually just to make things even more fun, I added the residual covariance, or Brown actually has a residual covariance. I know. It's depression and stuff is really what this scale is. But there is a residual covariance between items 1 and 2, and I'm putting a label on it. Now, a residual covariance, turns out that's a measurement model parameter, so that actually gets a different label between each as well, too. And to tell you which those questions are, depressed mood and loss of interest in unusual activities needed extra, basically, to make it fit. So everything up here, loadings, intercepts, residual variance, residual covariance, different labels within the C parentheses. Right? Then we get to our structural model where there is one factor, so depress. Its variance we can set to be equal across groups here, right in front of it with the double tilde. Now you'll note when I put a number there, that fixes the thing to the number, right? And I don't know if I showed this to you previously, but when you put a number times the parameter, you've basically set that parameter to that number. And the same thing goes with the factor mean. We put zeros in the label and it multiplies a zero to fix it to zero for both. How's this sitting with each of you? I use the Lavon command on this one. Why I use Lavon? Lavon, remember, is not shorthand. It's not a shortcut. CFA is the shorthand. Why I'm using Lavon here is it's forcing me to label all my parameters because each of these I'm going to have to test in my invariance model. So this allows me to not forget something. And you know me, you've had me for almost the entire semester. I forget a lot, right? That's the Spirit Airlines semester here. This is exactly right. Thank you. This is my motto, yes. Didn't mention that it was also
We'll
one.
get there.
We will get there one way or another. So I'm using Lavon. In Lavon, again, you can all the other values submitted to Lavon are the same. Remember, the Lavon syntax makes you specify everything, but I'm doing that again because I have to go and test everything anyway. So it's going to have to be verbose, lots of characters. But again, the last variable is the name of the grouping variable in your data, right there. Yeah.
Could you have two categories? For example, you're using sex and say eye color or something like that.
Yep. I'm not as familiar. In the old days, you'd have to make 4 categories. But Lavon may have made that easier. I haven't. You have to look in their syntax. Yeah. But yeah, the original versions of this would be, yeah, you can make as many grouping variables as you want. You just got to keep track of them. Yep. So we spit out our analysis. This is our configural model. What are we looking for here? Well, this is actually testing the covariance matrices between groups. Actually, I was testing the mean vectors too, right? So here, we want to see good model fit. It says the configuration is the same across groups. And it's okay. I mean, we've got our RMSEA of 0.04, CFI of 0.965, not 0.952 for TLI. Good enough. If it's not good enough, then I'm leaving. But you can see now it outputs your group in the label, right, for each. And so these are the loadings and parameters for the female group and the R square even. And then you go down to the male group and you get the same. Okay, so far so good? Questions? Okay, going from one to the other, buckle up those seatbelts. This is the only time it's actually, this will be the only time it's interesting. After that, it's tedious. So you'll note in my code, future self is really pleased with previous self on this one because I denoted each of the sections. And I did so because that's the order we're going to go in throughout. Right? So first, we're going to set the factor loadings to equal, otherwise known as metric invariance or weak invariance. Okay? So to do that, the loadings just drop that last letter. So before it was L1F and L1M. Now it's L1 and L1. So when Lavon sees the same values there, it assigns the same parameter to each group. Okay?
Sorry, can you go over that just one more time?
Absolutely. When Lavon sees the same label on either side of this C function, it assigns the same value to each group. So here, the loadings are all set to be equal. So that gives us 9 more degrees of freedom in our model. 9 more freed up parameters by equating them. But remember what we have to do with the factor mean. In the group that's not our, well, in one group we have to set the factor mean to 0. Actually, we're setting the factor mean to 0 for both. But in one group, we set the factor variance to 1. And we'll call that the female group because it comes first. And then just arbitrarily. And then the other group, we're going to estimate it. So when we want to estimate a variance, but we don't want to label it, that's where we might put NA. That's where we will put NA into the C parentheses.
So is NA a built-in code for it to understand?
Yes. So NA cannot be a label. NA is reserved for special meaning, and in R we know an NA means missing data. So technically, well, I don't want to get into R first. Yeah, good question. So what can show up here is a label that's not NA, so character or numbers. I'm sorry, character first followed by numbers is a label. It could be a number which sets the value and doesn't estimate it, or it can be an NA which estimates the value for that group. Okay? Any questions on the syntax? Syntax changes? Okay, so what we've done is we've not estimated 9 loadings, but did estimate 1 factor variance. So this model should have 9 minus 1, or 8 fewer parameters than our first model. Right? And we can actually tell with that, right? This model had 57 parameters. If I scroll up, pardon the scroll, 56? I shouldn't have done that. Oh, pardon me. 57 parameters, but 9 equality constraints. That's the difference. We are going to see this difference of 8 in our likelihood ratio test. It's the number of degrees of freedom that are different between the two models. But let's take a look at model fit. Now, this is an interesting situation. Depending on a couple factors, your model fit may or may not be relevant here, depending on your size of your data, depending on who your reviewers are. Some people will look at change in model fit to evaluate whether the metric invariance holds. So we can see before, our RMSEA before was 0.048, and in this model it actually got better, it's 0.043. So what this is indicating to me is that, okay, it probably holds, but a better way of looking at this to really test it is to do the likelihood ratio test. So I use the ANOVA command. I put my Lavon object, the result of the Lavon command, on either side, and it returns to me a chi-square difference test. Now, when you report this, we do typically report the method on it because it's a little bit different in category in the data with the robust maximum likelihood. But here, this difference says it's a p-value of 0.83 with 8 degrees of freedom. That's the 8 parameter difference between the models. So what is this telling us? They're not different. Remember, the null hypothesis is that they're equal. The alternative is at least one's not. We cannot reject our null hypothesis. So we've achieved metric invariance across the groups. It's a positive step. It's very negative if you have a lot of items and you have to go and figure out which one. But stay tuned. Questions on anything that I just showed you? Okay, let's move on to scalar invariance, the next block, the intercepts. Now, I will note, because none of these were non-invariant, I don't have to change anything, right? If one of them was non-invariant, I might have to go and put different labels in to allow that one to be different across groups. But because none of them have, I just go and test all of the item intercepts at once. So I've changed the label from I18F and I1M to just I1 for item 1, similar to all the other items. I go down, and now in my factor mean, my first group I set the factor mean to 0, and the second group I estimate it by indicating an NA. And then I look at my model fit. Again, it's not that much worse or different, but really I want to get down to the likelihood ratio test. And now with likelihood ratio test, you will note the p-value is 0.1343. So I don't reject my null hypothesis that the intercepts are equal. So I say, hey, the intercepts are equal. We've achieved strong invariance across groups. Not bad, right? We can also show the following, right? So remember the very first, the test of the configural model and the factor loading or scalar model showed there wasn't a difference between the two. And then this time I took the factor loading model and the item intercept model and showed there was no difference. So this next step, I actually compared the configural model with our current model, and it's still no difference, even though there's 16 differences in parameters. We should see that, right? So this is like saying, once I established the loadings were not equal or were equal to each other, I could just have moved on to the scalar estimate model. But because configural says they're roughly equal, I should see no difference here too. So anyway, sort of a daisy chain of these. Um, yes. Mm-hmm.
If the P is smaller than like 0.05, you can reject that now. Like that was the type like if it's like larger or greater than 0.05, it seems to me we still don't have evidence that the two models are like if you don't know the power.
Correct. That's the hard part. What will end up happening is the p-value will be very sensitive to group differences, but the power it can be a very powerful test. It can indicate group differences that are practically meaningless. So what you will end up seeing people try to do to avoid the power issue is to look at difference in model fit based on like RMSEA or CFI and TLI, because these effectively control for the sample size that you may have. Now, I don't necessarily know what's the best way of doing it, because here in the RMSEA and the CFI TLI, you'll see people say, oh, if the difference is like 0.01 or different. Well, that seems incredibly arbitrary, right? It's hard to know what the level is. Second to that, the remedy to all of this, again, is the modification indices. And I did just notice that they didn't print out, which I was afraid of, which I will show an old version and then fix this by tomorrow for everybody online. But this modification indices all rely on hypothesis tests. So now you're in a spot where, okay, residual covariance is what you have left effectively. Which one seems to have the biggest normalized residual potentially? But it's still harder to tell. So how I'm trying to answer your question is, yes, you're right. There's a lot of problems in looking at a p-value for it, but it's equally difficult to determine what a big effect size might be. Does that help answer a little bit?
Yes.
Thank you. So just for fun, I decided to go and try to get this modded indices. And this is what I was telling you. Somewhere between where I made these slides and where we are now, I'm supposed to use a different function, lav test score. So I'm going to go back to my previous slides because the output of the new function is pretty much the same as the out. I'm going to describe you, again, on my previous slides, what this looks like, but I'll update these slides with the new function when I get done. Yeah.
Is that a maximum of 10,000 iterations? Or what is that?
No, that tells it return all the modification indices, because it had before this used to have a catch that would only return,
Like first time.
or anyone that had a MI value bigger than 10. And for teaching, I wanted to show all the values, right? So
Oh, gotcha. Thank you.
yeah, you're welcome. Let me get up my webpage real quick. This one. You can see how different these are. I don't believe they're different at all. But, we are doing this one right here. So now, here we go. These are the modification indices. Of course, it has an error in it too. That's funny. I'll get this fixed. Basically, what I was going to tell you is the modification indices aren't large, okay? Of course. Now the future self is displeased with my previous self. Hey, Templin from like 2016, F you, man. What's your problem? So, if any of you can invent a time machine, tell my old self that I said this to my new self, or to him. Never mind. Anyway. Oh, there you go. Yeah, you never know. This class may not exist then, right? And then all of a sudden we just broke the system and we're done. What I'm saying here, if you look at the modification indices for the intercepts only, right, you'll see not many, if any, are very big. You've got a 3.29 here, a 2.68 there, and those are the same item. So the worst it got gave us a value, again, 3.84 is the thing I'm looking for this MI column. It's not close to that, right? Okay, but just to show how it works, I did allow that item to be non-invariant, right? Because I wanted to show you how it would change. So let's imagine item 7. Now, again, item 7, that's this one right here. This one right here, they had the largest modification index on the intercept. So I changed the label again to add back the F and M, allowing those to be different for that item on the intercept. Now, I don't go all the way back to the loadings. I already established the loadings were equal. I leave those to be equal. This item just has different intercepts. Okay? Okay. When I do that, I also added in, just for fun, a new parameter. Remember, the new parameter in Lavon is the colon equals. You saw this in the indirect effects section of path analysis. And I'm taking the mean for female minus the mean for male. This is going to give me effectively, sorry, not the mean, the intercept for each. What is the hypothesis test? What is the value of the group difference? This would be something I could turn into an effect size. I can turn it into a standardized estimate, right? And get a standardized estimate. So I fit this model. You'll see the fit does get better because I just freed a parameter. And if you look at the group differences, I can come down to this model parameter here, and we believe the female intercept for this item was 0.337 points higher than the male, and we standardized the latent variable for it. We would see that that's 0.377 with a p-value that does suggest there is a difference between the two. So when I'm saying this, I'm talking about standardized units. If you're trying to, no, I'm not even saying that either. So yeah, but this is sort of where you can get at a little bit of an effect size if you kind of convert some of these numbers into effect size type measures. And I will also note that here when I add, so I'm now doing an ANOVA with my all intercepts equal versus my all intercepts and metric estimates is all loadings equal. Scalar estimates is all intercepts equal, right? Scalar estimates 2 is where I let this one parameter be unequal. And how we read this is the first two lines, the p-value comparing the first two lines is right here. So when I let my intercept be not equal, I have a little difference, no difference statistically, but when I let that last parameter be not equal, you see that value there. And now I'm actually wondering, is that different in our new estimates? Nope, that's the same. So what have I said here? This is further evidence that this parameter should actually be different across groups. That's what I'm getting to.
Does that also indicate that maybe 3.84 is semi-arbitrary for the modification?
It is. Yeah, very much so. Yeah, and that's the thing. Modification indices are estimates as well too, right? So sorry to look at the time. I'm just like, I got 12. We're on, no, not with you. I'm not, sorry. I'm like, oh, how many more of these do I have? It's tedious. But can you guess what's going to go on with the residuals? We're going to now look at residual variances right here. Now, because I freed the intercepts for item 7, I'm not even bothering changing their label, letting them just be unequal. And then constraining each of the other residual variances to be equal. Here, I'm leaving the residual covariance apart. You could probably combine them all into one step, but I just separated it out. Let's go look at that likelihood ratio test. The likelihood ratio test, the p-value is very high, so we say, oh, no difference. Or another way of putting it, we have equal residual variances in each group.
Except for the one that we allowed to vary, correct?
That's right, except for that one, potentially. But even that one, I didn't actually make a test of hypothesis. But that's true. That is not equal, not necessarily equal. Okay, so now let's go and test the residual covariance. So I set the label equal. I scroll all the way down, and I should find a 1 degree of freedom. Where did it go? Nope. Here it is. My 1 degree of freedom test. It suggests potentially it might be we will leave it separate by group. So what it's telling you, so we may have a residual covariance that's different by group. It happens. But now we do have measurement invariance is complete. The measurement model is done now. And we have achieved partial measurement invariance, meaning every item but item 7 is invariant, and we let item 7 be non-invariant with respect to intercept and residual variance, and potentially that residual covariance. Okay? Speaking of the residual covariance, actually, I want to go and see the size of it. 0.832 in the male group, 0.484 in the female group. So it is a bit different. And actually, if I standardize that, 0.832, actually 0.456, 0.266. So even the standardized value, they're a little bit better with the standardized value, but not that much. All right, let's talk about structural invariance now, right? So now we're going to see, are there now group differences in the mean of the latent variable? So are men and women more or less depressed on average? And is there group differences in variation, in the variance of it? Right. So let's start with the variant. We're going to start here with the variance first. Now this is interesting. Our model that we enter this structural invariance into with, our last model that we estimated, has a different mean and a different variance by group. So this model now becomes the saturated model of the structural model. Right? Because each group has as many parameters as possible. So when we go and now test the variance, I'm going to not estimate the second group's variance. I'm going to set it to 1, and we're going to see what happens. Right? So I set it to 1, and we do our likelihood ratio test, and we see that there's a big p-value. So the variances want to be different. And did not create that. All right, and then we get to the factor means. We do the same thing. And actually, I noticed here, I'm a little dissatisfied with myself. The variances want to be different, but in my code, I fixed them back to be the same. So let's not do that. All right, so we can just rerun this. I put an NA in the spot where they should not be the same. And now I come down to the factor mean. And here, I can tell there is a mean difference between groups. Actually, yeah, there we go. But let me go a step further and see how much difference, shall we? Should we get a mean? Should we label it and go to mean difference? Okay. That's not the right model. Thank you, Michael. I appreciate your enthusiastic support. Let's do that. Here, because I have to set 1 to 1 for identification, I cannot put a label there. But I can do something different. I can say, I can label this here. I can call this var dm, for variance of depression in male. All right? And then here I can call this mean DM for mean depression in male. And then it turns out the mean itself, this mean is the mean difference because the other one was 0. So now I'm actually coming back to why I did not label it before. Because what we ended up estimating was the intercept of male. Where is this? Where am I at? This is incorrect. Did I do this wrong again? I'm sorry, folks. Structural mean model right here. There we go. So this, because the intercept in the female group is set to 0, it's not set to 0. It's estimated. Hold on, this is not all. I gotta fix this. We're gonna fix this before as well too. Let me put these back to NA. It's treating the 0 as an actual character label when I do that, and that's not good. All right, so now we see that depression mean is 0 for the female group. The depression variance is 1. In the male group, the depression mean is actually negative 0.091. So men are less than 1/10 of a standard deviation lower on depression. Actually, the variance is 0.883, so it's not quite less than 1/10, but there you have it. Sorry for the craziness in my code there. But do you understand why that's a mean difference? Because the other mean is 0, right? So we subtract 0 from that and we get its parameter. Now, when it comes to the variance, we can see that the male variance is 0.883. The female variance was fixed at 1. So if we were to go and talk about that, what this means is men are slightly less variable in their depression scores and have slightly less on average depression, is what we're saying. What do you think about all that?
Good stuff.
Interesting stuff. Would you like to see how that changes? Yeah.
The order of your tests, could it be in any order that you choose, or does it have to be the order in which you did it?
It is now.
We could test the
So there's two answers. There's the statistical answer, and then there's the practical, how people have done it in practice. In practice, this is the way that people tend to do it. In theory, in statistics, I think you can probably combine sources across that sort of come together. So what I mean by that is when you do the factor loadings, you may be able to do residual variances because those all work on the covariance side. When you do item intercepts, do them by themselves. Those on the mean side. So if you think about what we're doing is we're testing multivariate normal distributions. The covariance matrix and the mean vector are independent. So in theory, that means the tests that go associated with them should be independent. Why I'm saying that is item intercept, therefore, could probably go in different order than factor loading or residual variance. That's all. I wanted to ask this. Let's see what happens. I know. Oh, God. The spirit air. Hey, wait. Hey, ladies and gentlemen, this is your captain speaking. Let's see what happens when I push this button. Spirit Airlines. Yeah, thankfully, I don't believe there's a safety difference in Spirit Airlines. I don't think that's the problem. Maybe the frills, but not the safety, right? I know I said that, and literally everybody's looking at me like, oh, God, here we go. All right, what I'm going to do is I'm going to turn off all of the non-invariant parameters and take a look at the differences in the factor mean and variance.
Can I just ask why?
Yeah, I want to show you what's the impact of non-invariance on our test. Like if you're doing this type of setup, this type of analysis, the first question that probably led to this would be, do men and women differ in their average severity to depression or scores of depression? All right. And so this next way that I'm going to conduct this right here, hang on. Trying to do it in a way that doesn't change my console so I can compare and contrast. Let's see if this works now. Okay. So now, when I do that, here's what happens. So the values on the right are controlling for differences in those parameters we saw. And the mean value goes from negative 0.9091, it gets smaller. It's 0.0113. It's not a lot smaller. It's trivially smaller, right? But that's because we were sort of on the boundary of when we were adding those parameters, right? Similarly, if we look at the variance goes up slightly. But what is happening in each of these terms is because here, what I had done was I had just allowed the item intercept. Here, let me do this. Just the item intercept. What do you think will happen here? The mean difference should be evaporated. The variance difference should still be there. That's pretty
Oh, yeah.
all right. Why? Because item intercepts indicate or change when we allow those values to differ, the factor means differ. But item intercepts don't impact the actual variances. So now, if I go another step and I say, oh, okay, I can see that. Really, the only parameter that was really needed to be all that unequal was our residual covariance. How much does that change everything? You would expect it to be a little bit closer. Again, 0.091 and so that was the parameter that was the biggest problem, and that sort of gets us that. What I'm saying is this is the values on the right-hand side is like our answer key. That's the way that our process arrived at. The values on the left-hand side, those are sort of an imperfect model approximation to get there. And if I don't change my labels back, future Jonathan will be very unhappy. Questions about any of this? Do you see how it's all coming together? All right, here's the thing that bothers me about this approach. And we mentioned hypothesis testing and other. We've just done a ton of hypothesis tests. And you think about the issues in sort of chained hypothesis testing. Andrew Gelman and his colleagues call it the garden of forking paths, right? Where if you think of each of these tests having a small chance of being wrong every time we do it, we might all of a sudden, just by chance, have taken a fork that led us down this pathway. So a lot of this is subject to heavy hypothesis tests. So a lot of people end up doing things like, okay, let's not use a p-value like 0.05, or let's really worry about effect sizes. But then it moves into a less objective sense as to whether or not you've achieved invariance or haven't, right? So that's another pitfall to it. So I don't want to not acknowledge that. That's what I'm getting at. And of course, you'll see a lot of other, like the bigger, now this is a nice 9-item example. It's on the edge of what's large for a class. In your data, you might have 85 items, right? Go figure. That's not going to go as well, right? That's going to have a lot of problems. And so there is also a problem of scale when you go from this size and scale up. So for instance, we have 2 groups, 9 items. What if you have 9 items and 35 groups? Other folks have done work on that, looking at it from a random effects version, effectively. Or group differences might be random. But that's, anyway, you can think about how to build this in. The bigger picture is once you understand sort of the slipperiness of our factors, slippery meaning there are some times where we have to go and identify them by fixing things, but then for other values, we might be able to let them be estimated, right? That's the biggest complication. After that, everything you learn about design and analysis of variance or regression, linear models, that still applies. So there you have it. Last chance for questions on any of this today. Yes.
Apply this to, say, different classes to see if the thresholds, et cetera, would stay the same for 2 different IRT models to see if it's actually, if it truly is going to be a threshold for everybody versus, was it my sample specific threshold that I calculated? So like for example, you have your combined your L1 too, so for, but that might be like 3 or 4 classes to see if that would hold.
I mean, classes of
Like classes of students.
students. Yeah, that would be.
That would happen, that they took all the same questions, but the same
Yeah, yeah,
threshold.
yeah, you could do that.
I mean, thinking about students.
No. But you could definitely do that. Yeah, yeah. And if you get to, I mentioned this before, multi-level structural equation modeling, and I said when I was talking about everything puts a factor on it. Well, one of the first steps in multi-level structural equation modeling is allowing a random intercept by item across the grouping variables.
Right.
And if that random intercept variance is not zero, in theory, you've just said, oh, we're violating measurement variance. And our grouping variable is actually our clustering variable because it's otherwise we have a zero variance on items, intercepts, for instance, right? So there are other avenues that this goes down. But. All right, well, I'm out of time, so I'll stop here. I would like to wish all of you a happy fall break. And if you celebrate Thanksgiving, happy Thanksgiving. If you don't, then, that's a holiday we all like. Be thankful. Telling people to be thankful for things, right? Isn't that forced gratitude?
The best way to celebrate is just eat your favorite food.
And it's a nice holiday because it doesn't really that divisive. Thankfully, it's like one group celebrates or not. You all can be thankful. But I oppose the forced thankful. If you don't want to be thankful, that's fine too. Be thankful. You don't have to be thankful. And have that happy Thanksgiving.